Hey everybody, this video lesson is going to focus on a concept known as percent by mass, and it's also going to talk about a couple of examples of questions that would be really useful that you know how to do moving forward in this curriculum and on the AP test. Mass percent of an element is basically if you take the mass of the element and divide it by the mass of the compound that it's contained in and then multiply by 100 and you get the mass percent. Now you don't want to actually multiply by 100%, you want to multiply by 100. But the point is, you can figure out how much oxygen is in water, for example, in mass percent. We'll do an activity on the next page doing some calculations of mass percent. So make sure you have your calculator ready. I mean, this is stoichiometry, so why wouldn't you have your calculator ready? We're not going to actually do stoichiometry in this video lesson, but this video lesson is part of the stoichiometry unit. So you get the picture. Next thing I want to talk about is something called the empirical formula. Now the empirical formula is if you take a chemical reaction and simplify it down to its lowest whole number ratio. The concept of empirical formula is most useful when we're discussing molecules and organic molecules, specifically in organic chemistry. But we can apply it to inorganic situations, like our style of chemistry that we're studying here in AP Chemistry is typically inorganic or non-living substances. But basically what you do is you take a substance that has numbers that can be divided, and you divide them by the lowest common factor and simplify the ratio. And so benzene, which is normally C6H6, simplifies in its empirical formula to just C1H1. That's the empirical formula. Now, ionic compounds always reduce themselves to the lowest whole number ratio, and so you never really talk about empirical formulas with ionic substances. You only talk about empirical formulas when you're talking about molecular or organic substances. So here's a pretty common and basic example of trying to calculate the percent of iron in iron 3 oxide. So you want a periodic table as well because we need to figure out the molar mass of the Fe2O3, and that's going to be on our denominator, and then we've got to figure out the mass of iron in that substance. Remember, the formula is the mass of the iron divided by the mass of the total substance. And so we need to figure out how much iron we have. Well, we have 2 atoms of iron, and each of those are 55.85 grams. Now, I put that on the top. Now, I need to divide by the molar mass. If I take 2 irons and add those to 3 oxygens, I get a mass of 159.7. Now, when I put those into my calculator and I multiply by 100, I'm going to get a percent. And the answer is 69.9%. That last one was just dipping our toe into the kiddie pool. This one gets a little bit more involved. Basically, what we need to do is order the molecules from highest percent oxygen by mass to lowest percent oxygen by mass. So we're going to have to do a number of calculations here. So I'm going to zoom in so I can write on here and give myself a little bit more room. And we'll just start on the left. So water has 1 oxygen, so that's 16 grams, and the mass of water is oxygen plus 2 hydrogens. Well, hydrogen is 1.01 and oxygen is 16, so my answer here is 18.02. Now, if I put this in and multiply by 100, I get 88.8%. That's a pretty high percent by mass oxygen for water. But is it the highest? Well, we'll have to figure that out. Next one I want to do is N2O. So again, I have 1 oxygen, so I have 16 on top, and underneath I have N plus N. Now, each N is about 14, so 14 plus 14 plus 16 gives me roughly 44.02, and I multiply that by 100 and I get 36.3%. So a little bit less, well, much less, in fact. Now the next one is going to take a little bit more calculations. Now I have 2 oxygens, so 2 times 16 on top. Now underneath, I want to add up 3 carbons, which is 3 times 12, plus 6 hydrogens, which is 6 times 1.01, plus 2 oxygens. And when I do that, I get a mass of 74.08 grams. Now when I take those 2 and divide them and multiply by 100, I get 43.2%. Okay? And finally, carbon dioxide. Again, I have 2 oxygens, so 2 times 16 on the top, and then the mass of carbon is 12.01, so 12.01 plus 16 is 44.01 grams. Well, I take those 2 and divide them and multiply by 100 at the end, and I have 72.9%. So now that I have my numbers, I can put them in order. So rank them. The highest would be water, followed by carbon dioxide is next, followed by this substance, C3H6O2, and finally N2O4. So in summary, I had to do 4 different calculations of percent oxygen by mass and then rank them from highest percent by mass to lowest percent by mass. What I forgot to mention is that you can overlook the 100 grams of the original substance because it says consider separate 100 gram samples of each. Now if they all have equal mass, then you really don't need to care, or you really don't need to worry about the amount that you start with. But read the question carefully, because sometimes the way that the question is worded might ask you to do some percent by mass calculations, but the answer won't necessarily be ranking them. It might be a little bit more nuanced, so make sure you read the question carefully. Here's an example of the most involved percent by mass type question that you're going to see here in the video lesson today. Let's take a look at the problem. It says a composition of adipic acid, which is 49.3% by carbon, 6.9% by hydrogen, and 43.8% by mass. What's the empirical formula? So basically, we know it has carbon, hydrogen, and oxygen in it, and we know that they are in a specific ratio, but all we are given is percent by mass data. Well, we can figure this out. It might not seem obvious to you at first, but what we're going to do is assume that we have exactly 100 grams of the unknown substance. By assuming that we have 100 grams, what it does for us is change our percentages into masses. Because if we have 100 grams of total substance and 49.3% of that 100 grams is carbon, then I know that my substance is 49.3 grams of carbon. I also know that it is 6.9 grams of hydrogen, and I also know that it's 43.8 grams of oxygen. The next thing I'm going to do is I'm going to convert each one of these masses to number of moles of that substance. So I'm going to use the molar mass of carbon to convert to moles of carbon, use the molar mass of hydrogen to convert to moles of hydrogen, and molar mass of oxygen to convert to moles of oxygen. And once I've converted these masses into moles, then I can use the mole to mole comparison in order to figure out the empirical formula. Because whenever you're asked a question, what's the empirical formula, what you really are being asked is compare the moles of each of the substances that make up the unknown substance. So I'm going to take the grams of carbon and I'm going to multiply by 1 mole over 12.01 grams. And I'm going to divide those two numbers and I get 4.10 moles of carbon. Next, I'm going to take 6.9 grams of hydrogen. I'm going to multiply by 1 mole of hydrogen over 1.01 grams. And I get 6.85 moles of hydrogen. Finally, I'm going to take 43.8 grams of oxygen and divide by the molar mass of oxygen, which is 16 grams, and I'm going to get 2.74. So now I have a mole to mole to mole comparison of carbon, hydrogen, and oxygen. Now I'm on to the last step. Take these numbers now and divide them all by the same number, and the number you want to divide them by is the smallest number of moles that you see. And as I can see, the smallest number of moles is 2.74 moles of oxygen. So if I divide this one by 2.74, it equals 1. If I divide this one by 2.74, my ratio turns into 2.5. And if I divide this one by 2.74, then my ratio turns into 1.5. So now I have this ratio of 1.5 parts carbon, 2.5 parts hydrogen, and 1 part oxygen. But I know that I can't keep half molecules in the empirical formula. They have to be whole numbers. And so in order to get rid of the fractions, I just multiply each one of these by 2, and my final answer is carbon with 3, because 2 times 1.5 is 3, and then I go 2 times 2.5 is 5, so hydrogen is 5, and then oxygen is 2 times 1, or 2. So my final empirical formula for adipic acid is C3H5O2. In summary, I assume 100 grams of substance, and that turns my percentages into masses. So now I have masses of the same substance. I divide them all by their molar mass to figure out the moles of each. Then of the moles that I see, I divide by the smallest number of moles of the 3, and I get a mole to mole to mole comparison. Usually when you divide by the smallest number of moles you'll come out to a nice number that is either like a half mole or a third mole or even a whole number. And then you may need to do some final adjusting to figure out what you need to multiply those molecule comparisons by in order to get whole numbers. And in this case, I had to multiply them all by 2 to get rid of the fractions. But my final empirical formula was C3H5O2. To To finish up this problem, let's answer the second question. It says, in a separate experiment, the molar mass of adipic acid was found to be 146 grams. What is the actual molecular formula of adipic acid? Well, let's go back to the empirical formula up here. If I calculate the empirical formula of the adipic acid, and I take 3 times 12 plus 5 times 1 plus 2 times 16, that would give me a molar mass of the empirical formula of 73 grams. If the molecular happens to be 146 grams and the empirical is 73 grams, then if you take those two and divide them, then you get a 2-to-1 ratio. So essentially what that means is that the molecular formula is twice the ratio of the empirical. So if I take C3H5O2 down here and I multiply it by 2, then what I get is C6H10O4. And that is the molecular formula of the adipic acid. By comparing the molar mass of the empirical to the molar mass of the known molecular, then I can figure out the ratio, which I have to multiply by my empirical formula by in order to get the full molecular formula. In this case, it came out to be 2. But sometimes the molecular formula is 3 times the empirical or 10 times the empirical. Well, if that's the case, you figure out your factor and then take that factor and multiply it by the numbers in the empirical formula to come up with the final ratio of the different elements in the molecular formula. Well, that takes care of this video lesson. Thanks for watching.